Hello, everyone. Welcome to Lecture 17 on Introductory Statistics. Now, in this lecture, we are going to talk about hypothesis testing. In Section 1, we are going to mainly focus on basics of hypothesis testing. Now, let's move on to Section 1. Okay, so in many cases, we are interested in answering questions such as the following ones, right? So, is the global temperature increasing? Did the new Super Bowl ads actually increase sales? Has teenager smoking decreased in the past 5 years? Is the new treatment more effective than the traditional one? So these are types of questions we are constantly have in every day. And in this chapter, we will learn a statistical method called hypothesis testing to address these type of questions. Now, what is, firstly, let's consider this definition. Now, in statistics, a hypothesis is a claim or statement about a population parameter. Now, a hypothesis test is a procedure for testing if a hypothesis is true or false. Okay, so now there are 5 steps in a typical hypothesis testing procedure. Now, one is state the hypothesis. There are usually 2 hypotheses. All right, one is called the null hypothesis. The other is called the alternative hypothesis. Second is choose a proper test statistic. Third is to compute the value of the chosen test statistic. Step 4 is do one of the following. All right, so one is the p-value approach. The other is the rejection rating approach. Now, I'm going to focus on the first one. All right, the p-value approach. And finally, you draw a conclusion, but be careful both statistically and non-statistically. We're going to talk about all these 5 steps in detail, but let's first talk about the first one, right? State the hypothesis. How to state the hypothesis, right? So one of the hypotheses is called the null hypothesis, all right? So what is a null hypothesis? Okay, let's focus on this one first. The null hypothesis, denoted by H0, is a claim about a population parameter that is maintained unless its contrary is supported by strong evidence beyond a reasonable doubt. Okay, so the mathematical form of the null hypothesis usually contains the equal sign, or usually contains the equal sign. Now, oftentimes, the null hypothesis has one or more of the following properties. Now, it often represents existing or pre-existing state, like a status quo, right? Status quo, okay? The null hypothesis is also usually a statement of no effect, no difference, and no change because it contains the equal sign, right? So no difference. This is usually the form of the null hypothesis. Okay, now the alternative, well, be careful, is a population parameter that is maintained unless as a contrary is supported by strong evidence beyond a reasonable doubt. Okay, now in hypothesis testing is really like a court trial. Now, now in a court trial, we have 2 hypotheses. All right, so one is the defendant is innocent. This is one hypothesis. Now, it's the contrary is going to be what? The defendant is guilty, right? So in such a case, you have to assume that the defendant is innocent. This claim is innocent, is maintained unless what? Unless there is a strong evidence against this defendant, right? A strong evidence beyond a reasonable doubt. Then you can say, all right, this person or this defendant is guilty. Otherwise, it must be remained as what? Innocent. It's called a suspect, right? It's called the suspect, but not a guilty one. Then the alternative hypothesis, right? So what is the alternative hypothesis? It's denoted by HA or H1 as the claim about a population parameter that is accepted as true only if there is a strong evidence in favor of it. Now, in the court trial, right? So you can only claim the defendant is guilty only what? Only if there is a strong evidence in favor of it. Okay, that's called the alternative hypothesis. Okay, so the mathematical form of alternative hypothesis HA can be one of the following, depending on different situations. One is with the inequality sign, with a greater than sign, and less than sign. They do not have the equal sign. All right, it's something different from the null. In many cases, the alternative have one or more of the following properties. It is contrary to the null. The null saying that it is the status quo. It is what? Nothing change, no difference, no effect, right? So it is contains the equal sign. That's null hypothesis. But for the alternative hypothesis, it is usually means something changed, right? Means something happened. It's not equal or greater than or less than, right? Something like that. It's often claimed that people believe to be true or feel suspicious of, right? You feel suspicious of. You feel suspicious of that the fact that the claim that the defendant is guilty. That's why this defendant is called the suspect, right? So if something we feel suspicious of, something we believe to be true. Okay. Now, the alternative hypothesis is really a statement. Sorry, this is not this. There is a fact. There is an effect. There is a difference. All right. And there is a change. Okay, that's something we have to be careful. All right, so sorry about that. There's typos here. There is an effect. There is a difference. There is a change. Now, depending on the alternative hypothesis, we have different types of hypothesis testing. Okay, depending on the mathematical form of the alternative, we have different types. So if the alternative hypothesis have a mathematical form containing the inequality sign, it's called a two-tailed test. If it is contain a symbol greater than, it's a right-tailed test. If it is symbol is less than, it's a left-tailed test. Now, right-tailed, left-tailed is called a one-tailed test. Okay, so one thing to remember this, if it is contains the greater sign, as you can see, this points to the right. Right, it points to the right, so it's a right-tailed. Okay, and less than as points to the left, so it is called left-tailed. All right, left-tailed test. Now, if it is equals, if unequal is not equal to, that can be both sides, right? Two-sided. Okay. Now consider this example. A corn seed company claims that the germination time for their product averages 11.3 days. Okay, this is what they claim. A farmer believes that the actual mean germination time has a different value and plans to test his belief. State the null and alternative hypothesis. What type is this hypothesis test? Okay, now solution here. Okay, so we have we want to state the null and alternative. So the null is denoted by H0, and the average that usually contains the equal sign. It is status quo. It is no difference, no change, right? So it contains the equal sign about the population. So mu equals 11.3, and the alternative is something they believe to be true, something they are suspicious of, right? So now the farmer believes what? Believes the actual mean germination time has a different value. Right? Be careful, it's a different value. So that means what they believe is mu is different from 11.3. So here, where what? Mu is the mean germination time, right? Where mu is the mean germination time. So this is the null, this is the hypothesis. Now, what type is this? So since what the alternative contains a not equal sign, this is a two-tailed test, right? Two-tailed test. Now, in this example, okay, so all right, let's consider another example. Okay, now the average floor size of houses in a particular county is 2,432.2 square feet. A housing agent believes that the average floor size has increased in recent years. State the null alternative hypothesis and what type is this hypothesis test. Okay, again, solution. Now let's define. Okay, let mu. Okay, mu be what? The average floor size in recent years. Okay, in recent years. Now, mu is going to be a parameter. It's about the population, right? So now the claim, the null hypothesis will be what? Will be something there is no change from the past, no difference from the past. It contains an equal sign. So that's going to be mu equals 2432.2. And the alternative would be what? Would be something that the person believes to be true. The agent believes what? The average is increased in recent years. So increased means mu now is greater than 2432.2. This is our alternative. So because what? The alternative contains this greater than sign that points to the right. So it is a right-tailed test. Okay, so this is another example. Let's consider another one. Okay, so health agency reports that the mean systolic blood pressure for males 35 to 44 years of age is 128. The medical director of a company believes that the mean should be lower than that based on the recent medical records of 70 company executives in this age group. State the null and alternative hypothesis. What type is this? Okay, so let what? Mu be the mean. Okay, what? This blood pressure, systolic blood pressure for males of ages 35 to 44. Let's say that. Okay, so the null hypothesis is contains the equal sign mu equals what? 128. Okay, the alternative is what? This medical director believes is lower than this, right? So its mu is less than 128. Okay, so therefore what? Therefore it is, because this contains the less than points to the left, so left-tailed test. Okay, all right, so we have introduce how to state the hypothesis and determine what type of hypothesis test it is, right? So it's very good. Now we are going to move on to the second step. It's about the test statistic. All right, so um, how to choose test statistic. All right, so as we know, the null hypothesis is maintained unless there is a convincing evidence against it. Unless the convincing is collected against this, we have to assume H0 is true. That's the basic assumption we have to follow for hypothesis testing, which is similar to a jury trial. We have to assume the suspect is innocent unless convincing evidence is provided against it. Okay, given data from a random sample, we obtain an estimate of the population parameter. The idea of hypothesis testing is an estimate close to the hypothesized value H0 gives evidence to the null because it's pretty close to the hypothesis value, which leads to a conclusion not to reject H0. Now, if we got an estimate far from the hypothesis value H0, this will give evidence to the alternative, which leads to a conclusion to reject H0. Okay, so to be more specific, if the test is left-tailed with this one, then reject H0 if X bar is far to the left of mu0, right? So if it is right-tailed, reject H0 if X bar is far to the right of mu0, and is far away from either direction. Okay, so we're going to talk about these three different situations using example. So if I guarantee you, you will be clear when we talk about those. All right, so let's just leave it here for now. Now the test statistic, what is a test statistic, right? So we want to choose a proper one. Okay, now for this section, we're going to, for this chapter, we're going to mainly focus on three different situations. One is a large sample z-test, small sample z-test, and small sample t-test. Okay, so we have the following four different situations for the mean. So it's depending if it is a large sample or it's a small sample, right? So if it's a large sample, then then if sigma is unknown, you use this one. If sigma is known, use this one. For small samples, if sigma is known, normally distributed, we use this C. Otherwise, we use T here. Okay, so we are going to mainly focus on the large sample cases, but you also have to know the smaller sample cases as well. Okay, so now consider this example. Determine the test statistic and compute its value given the following information. A, the null is mu equals 23 versus the alternative mu is not 23. There are 35 observations in the sample with a sample mean X bar equals 24. So the population has a known standard deviation sigma equal to 3. So now one question is, is this considered as a large sample or small sample? Okay, so for large sample, all right, it's usually compared is greater or equal than 30, right? It is large. A large sample, all right? And also sigma is known. It's known, it's 3, right? It's known. So now larger sample, sigma known, so we use this one, right? So we use the second one, right? So we use the second one here. Okay, so it's z equals x bar minus mu of 0 over sigma over square root of n. Oh, okay. One question says, what is this is sigma 0? Mu 0. Okay, what is mu 0? Now mu 0 here, all right, so mu 0 is the hypothesized value in H0, in H0. Now, for instance, in H0 here, mu equal to 23, so the hypothesis value is 23 in H0. So mu 0 equals 23 here. So we are going to 24 is the bar minus 23. Sigma is 3 over square root of 35. And then you can use a calculator to find this one. But when you use a calculator, be careful, right? You want to use the parentheses, all right, for the top and the parentheses for the bottom. Okay, so be careful when you use a calculator, right? So using the parentheses, and then you should get some value here. Okay, so I'm going to skip that. B, okay, B. The null is mu equal to 5, alternative mu greater than 5, n is 15. With sample mean and certain sample standard deviation, the population is normally distributed with the unknown standard deviation. So for this one, n is a larger sample or small sample. So it's less than 30, right? So it is a small sample. And sigma is unknown. As unknown, right? So we do not know the value for sigma. And we know it's normally distributed. So then this is a small sample, sigma unknown, normally, okay, it's t, right? It's t. So t equals x bar minus mu of 0 s over square root of n. So plugging all the value, is 4.5 minus mu 0 here, hypothesis value is 5. S is 0.4 over square root of 15. Now you use a calculator, right? You can calculate this one. Okay. C. The population we all know is mu is 60. Alternative mu is less than 60. 15 observations, sample mean, and population normally with a known standard deviation. So very good. N is 15 and less than 30. So small sample. And the sigma equals 5 is known. Okay, so therefore what? Z equals, well, for this one, because we check the table, right? So let's check the table. Now it's going to be the third case. Since sigma is known, so we use Z, right? We use Z here. Use this one. So we're going to have Z equals x bar minus mu 0 sigma over square root of n. So it equals x bar is 67 minus 60 over 5 over square root of 15. And you can calculate this value. B, mu h0 is this, h null, okay, 120, and sample deviation is unknown. So since n equals 120 is greater or equal than 30, it's a large sample. Okay, and sigma is unknown. We only know S, right? Sigma is unknown. So we're going to use Z equals what? Z equals x bar minus mu of 0. It's going to be S over square root of n. So it is what? 30 minus 33. S is 25 over square root of 120. And you can find this value. So that's basically what we do, right? To choose the proper test statistic and calculate its value using what? This table, right? Whether it's a large sample or small sample, right? As if what? Sigma is known or unknown, right? So very simple. Okay, now this is called a significance level. All right, so what do we mean by a significance level? So the purpose of hypothesis testing is to make a choice between the following two decisions. All right, so one of them is the evidence from the data is insufficient against H0. So in such cases, we fail to reject H0 and therefore do not accept HA. Now in the court trial, right? So we may defendant is innocent is H0, defendant is guilty is the alternative hypothesis. Now, if the evidence against the null hypothesis, which means the defendant is innocent, is not enough, is not strong, right? Then what? You cannot claim the defendant to be guilty. You fail to reject H0, and therefore you cannot accept that this defendant is guilty. So that's the first choice. Now another choice is the evidence from the data is sufficient against H0. In such case, we reject H0 and accept HA. So for instance, in the court trial, if the evidence is very, very clear against the null hypothesis that the defendant is innocent, right? It's very, very strong evidence against this defendant. So we are going to say, okay, you are guilty, right? Put to jail. Okay, so that's the second choice. Now we need to make one choice between these two, right? So now sometimes you need to make a firm decision, right? Whether to reject H0 or not. You accept it or fail to accept it. You reject it or fail to reject it. Okay, so now to prevent some subjective judgment, right? We usually what? This firstly set a threshold of some kind in advance. As for how much evidence against H0 is, sorry, okay, sorry about that, okay, is needed, okay, is needed to reject H0. This level of significance is utilized here to set such a threshold. Okay, so now what is the level of significance? Now, level of significance alpha is a probability value used as a cutoff for determining whether the sample evidence constitutes sufficient evidence against H0 if H0 is assumed to be true. Oh gosh, this is a really long definition, right? So it is a probability value set in advance to control the probability of mistakenly rejecting H0 when H0 is in fact true. Okay. Common values of alpha is 0.05, 0.01, and 0.10. That is the significance level. Okay. Well, the significance level alpha is usually set and declared in advance because you don't want to have any ambiguity. You want to set it in advance, right? The significance level is set there. That's the significance level. Two approaches. One is the p-value approach, the other is the rejection rating. I'm not going to talk about rejection rating in this talk. We're going to focus on the p-value. So what is the p-value? The p-value or the observed significance, okay, of a hypothesis is the probability computed under H0 that the test statistic would take a value as extreme as or more extreme than in the direction of HA, the value actually observed in the data set. Okay, so so that is the p-value. Right, the p-value is actually probability. All right, probability under H0. Okay, that the test statistic would take a value as extreme as or more extreme than in the direction of HA, the value actually observed in the sample data. Okay, we're going to illustrate this one in the example later on. Okay, so now the p-value to be more specific. All right, so we separate them into three parts. For three types of hypothesis testing, we have these three ways to find them. All right, one, if it is left-tailed, all right, with the alternative is less than mu0, right? The p-value is the area to the left of the observed value of the test statistic under the density curve. Okay, as you can see from this one, the p-value is, after you calculate the test statistic, the p-value is simply this area. Okay, it's the area to the left because it's a left-tailed test, right? It's to the area to the left of the test statistic. Now, if it is a right-tailed test, the p-value is going to be the area to the right of the test statistic. Now, this is the second case, all right? So for the third case, if the test is the two-tailed, all right, you firstly find the absolute value of the test statistic, and then the p-value is twice the area to the right of the absolute value of under the curve. Okay, so I'm going to leave these ones here for now, okay? And then later on, we're going to show several examples about this. And I hope by then you will be clear about this, okay? So let's leave it here, okay? Just remember, there are three different cases, all right? So three different cases: left-tailed, right-tailed, and two-tailed. Okay, let's just move on. Now, here is a decision rule, right? Conclusion using the p-value approach for any hypothesis test. If the p-value or the observed significance is smaller than the significance level alpha, we conclude that there is sufficient evidence to reject H0 in favor of HA. So what does that mean? That means what? 1, right? So if the p-value is less than or smaller than alpha, right? The significance level. This is the cited significance level. The p-value is observed significance level. If the observed significance level, which is the p-value, is less than the level set ahead, then, well, be careful. Then what? We conclude that we reject H0 in favor of HA. Okay, 2. If the p-value is greater than or equal to, right? Or equal to alpha, right? So what do? We fail to reject H0. Fail to reject. This is the two decision rules, all right? Be careful. Now, for instance, let's consider this example. If the p-value is 0.023, A, do you reject the null hypothesis significance level alpha is 0.1? Do you Y? Okay, so in A here, what should we do? So it's p-value is what? 0.023. I believe it's less than alpha, right? It's less than alpha equals 0.1. So we're going to reject and in favor of HA, right? So we reject H0. Right? Do we reject it? Yes, we reject it. Why? Because what? The p-value is less than alpha. Now B, do we reject that signal at 0.01? No. Right? P-value is greater than alpha equals 0.01. Right? So we fail to reject H0 at this level. All right, so that is the conclusion rule, all right, based on the p-value. The rejection rating approach, I'm going to skip here, but if you're interested, you can read the textbook. I'm going to skip here, all right? So skip here. Now, here is a very interesting way of the types error. There are concepts, right? So it's the types of error. Now, the testing procedure in general is to take a random sample because it's taking a random sample, make a decision. It's not going to be always correct. It will make an error. Okay, so now in hypothesis testing, a type 1 error is an error to reject H0 when it is actually true. All right, so that is a type 1 error. So it is the H0 is true. However, you reject it. It's like the defendant is innocent. However, you reject it and saying that he's guilty. And that's the type 1 error. So what is a type 2 error? So type 2 error is an error when not to reject H0 when it is actually false. Right? So H0 is a false. This defendant is guilty. However, you fail to reject H0. So which means what? You say that it is this defendant is innocent. Okay, so that's going to be a type 2 error. So in this table, I'm listing it here. All right, so here is the decision. You may reject or fail to reject. And true nature, true state of nature. So H0 is actually true. H0 is actually false, right? So here, as you're going to conduct a type 1 error because we know that H0 is true. However, you reject it, right? So that's type 1 error. And for H0 is false, you reject H0. That's going to be good, all right? If H0 is true and you fail to reject, no, that's also good. However, if H0 is false and you fail to reject, this leads to a type 2 error, okay? So this is something you may have to be careful, okay? Now another example is going to be like my wife's birthday is let's say someday, right? My wife's birthday, say that it's uh, July 18th. Let's say that, right? Say that my wife's birthday is July 18th, right? This is the null hypothesis, all right? So if I'm coming, if I'm making a mistake, I say that my wife's birthday is not uh, July 18th, right? That's going to be what? A type 1 error. That's going to be a type 1 error because what? Because my wife's birthday is July 18th, but I made a decision saying that it's not. It's not. This is the type 1 error. Okay. See, that's a really serious problem, right? The type 1 error. This type 1 error is going to be a serious problem for me. Now, well, a type 2 error is something like, okay, my wife's birthday is not, because her birthday say is July 18th, so her birthday is not going to be any day else. However, I would say that, I made a decision saying that her birthday is July, say, 17th, right? July 17th. And I just bought a big cake, right? And the candle dinner and everything, right? So I set it up on July 17th, right? Instead of July 18th. Now, this is going to be a type 2 error because what? It is false, right? So her birthday is not on July 17th. But what I did is I say that it's July 18th. So July 17th. Now, this is going to be a type 2 error. All right, so I failed to reject it when it is actually false. Okay, so in this case, this error is not going to lead a biggest problem to me, right? And at least I prepared a lot of stuff for my wife. She will not be. She at least will feel better than the case that when I forget her miss her birthday, right? So that's gonna be a horrible situation. Um, so you see that there's a difference between the type 1 error and type 2 error. Type 1 error is usually more serious. Okay, type 1 error is usually more serious. Um, Now that is why people usually want to control, all right, the type 1 error. Okay. Now recall that significance level is a probability value setting. We want to control the probability to mistakenly reject H when H0 is true. Uh, um, since it's usually a serious error to reject H0 when it is actually true, we want to control this error rate, right, such as alpha is 0.05. Now, therefore, alpha can be interpreted as the probability of making a type 1 error in the hypothesizing procedure. Okay, so we give the following proposition without proof. Okay, so for hypothesis with fixed times, okay, a smaller value of the significance level alpha will have the effect of increasing the chance of making a type 2 error. Okay, in order to simultaneously reduce the rate of type 1, type 2 error, we must increase the sample size. Okay, so now let's just review these basics of hypothesis testing. There are 5 steps. Step 1, state the hypothesis. Step 2, choose a proper test statistic. Step 3 is compute the value of the chosen test statistic. Step 4, well, we are going to focus on the p-value approach, or just the p-value approach, compute the p-value of the test. And the 5 is draw a conclusion, both statistically and non-statistically. Okay, so now let's just do some examples about this one, right, in section 2. Now we learned how to state the hypothesis, and the next key is choose a proper one. Now here we are focusing on the larger samples, right? So if we have a larger sample with n is greater or equal than 30, then these are 2, all right? So if sigma is known, you use this one. If sigma unknown, use this one. Okay, now mu0 is a hypothesized value of mu in the null. Sigma is the population, S is the standard deviation, sample standard deviation, and approximate standard normals. That's why it's called a z-test. Okay, so this is a p-value approach, as we stated before. So 3 different cases, right? The left-tailed, right-tailed, and two-tailed. So we are going to come back to this slide later. The decision rule as well, we discussed it. So if the p-value is less than the significance level, reject the null in favor of the alternative. If the p-value is greater than or equal to the significance level, fail to reject H0. In the end, restate the decision using simple and non-technical terms. That is, state a final conclusion that addresses the original claim so that anyone can understand it. So here is going to be a statistical conclusion, and the last one is going to be a non-statistical conclusion. Okay, the rejection region I'm going to skip here. Okay, decision rule. Okay, now let's consider this example. Assume that the body temperature of healthy newborn babies have a standard deviation sigma equals 0.65. 32 years ago reported the mean temperature is 98.6. Researchers at the local health institute believe that mean temperature should be less than 98.6. They recorded body temperature from a random sample of n equals 93 healthy newborn babies and obtained a sample mean of x bar equals 98.52. Is there sufficient evidence in the sample to indicate that the researchers' belief is correct? Assume the significance level alpha is 0.05. Okay, so I'm going to use the p-value approach. All right, so now state the hypothesis. Now we know that there are 2 hypotheses, right? So now let what? Now we are really interested in what? The mean temperature mu, right? It's about the healthy newborn babies. Yes, the researchers believe that mean is should be less than that. So we know that the null is contains the equal sign. All right, so mu equals 98.6 about the population, right? It's okay. Be careful. What do we have? All right, is the hypothesis is always about the population. It's never about the sample. Okay, so here we have this statement. All right, the mean temperature of a healthy human is 98.6 Fahrenheit. This is about the population. Okay, so mu equals 98.6 versus what? The HA, mu is not 98. Oh, well, sorry, there's something different. Right, mu is what? They believe is less than, right? Mu is less than 98.6. Okay, mu is less than 98.6. This is something that they believe to be true, right? They are suspicious of. It do not contain the equal sign. It is less than, right, 98. So that's the alternative hypothesis. So you have to be very careful on this. Now, the null and alternative is a claim about the population. It's never about the sample, right? That's why we are using 98.6 instead of the sample mean, right? 98.52. Okay, so be careful on that. Hypothesis is about population, not about sample. So these hypothesis value should be 98.6, which is about the population. All right, not 98.52, which is about the sample. Okay. So let's state the step one. All right, step two. So choose a proper test statistic. So now, do we have a larger sample? N equals what? 93 is greater or equal than 30. So it's a larger sample, right? Now another one is sigma known. All right, I know that sigma is known, right? Sigma equals 0.65 is known. So we can use that one. So we're going to choose this one is x bar minus mu 0 over sigma over square root of n. So this is going to be our chosen test statistic. Then we compute its value. So we can just write this one here, x bar minus mu 0 over sigma over square root of n equals, now x bar is given here, 98.52 minus mu 0. Mu 0 is the hypothesis value in H0, so 98.6. And sigma is, what is sigma? Sigma is 0.65. Okay, 0.65 over square root of n is 93, so 93. Okay, so you can calculate this value. Okay, what is this value? All right, I forgot this value, but you can calculate this value. All right. Oh gosh, I should calculate this value. Let me get my calculator. All right, this is very important. Let me calculate this value. Let's see if I can find a calculator. Gosh, my calculator is out of power. Okay, so not good. Okay, doesn't work. Well, anyway, I'm gonna put there. Okay, and then okay, enter a calculator here in Google. Well. Okay, let me use my cell phone. Okay, I'm gonna use my cell phone to do that. Okay, all right. Okay, let me do that. Okay, 98.52 minus 98.6. So this is what? negative 0.08 and 0.65 over, oh gosh, square root. Where's square root? Oh gosh, this is horrible. Okay, let me use a Google calculator maybe. 0.65 over square root. Okay, let me do this. 93 raised to power 0.5. Okay, all right, I got it. So this is 0.0674. Okay, so let me do that again then. It's going to be 0.0674. Okay, so I got is negative 1.187. Okay, so that's good. All right, then the p-value. Now let's see what is the p-value. So in order to use the p-value, remember, we need to see based on the type, right? What type of this hypothesis? Since this is less than, right? Less than this. So this is a left-tailed test. All right, so the p-value is, okay, so p-value, since it's a z-test, it is a probability for capital Z less than negative 1.187 equals, all right, normal CDF, okay, so this is going to be what? Negative 10 to the power 99, negative 1.187, and this is 0, and this is 1. Okay, using the calculator, we should be able to find this one. Okay, let me just use a normal calculator. Okay, sorry about that. Okay. Okay, so it's a negative 1.187. Okay. I mean, yes, calculate. Okay, so we found this is a 0.118. Okay, so draw a conclusion, right? So since what? Since, well, let me just show you why I have this, or since the left tilde test, and in our, okay, in this one, it's a left tilde test. So this is the area of this area. So that is what the probability for capital Z is less or equal than this value. All right, this is reserved values lowercase z. Okay, so that is this area. Okay, that's why we are having this p-value equals, right, the less than the test statistic, right? Because it's a left-tilde test, and therefore we have this. Now, if we draw a conclusion, now since what? The p-value is, now this is 1.118. Now the significance level is 0.05, and the p-value should be what is greater, right? It's greater than alpha is 0.05. So if it is greater than alpha, so what do we do? Remember, the decision rule, right, is greater than fail to reject, right? Fail to reject the null. So we fail to reject H0. Okay, and we need to, this is a statistically, right? The statistically conclusion, right? And we also do some non-statistically conclusion, right? So there is no sufficient. Well, okay. So this is also statistically, or you can say there is no sufficient evidence to reject H0. Okay, you can also do this. All right, this is also statistical conclusion. Now, you also have to do that non-statistically, which means you need to state this conclusion such that anyone can understand that. Okay, so mm, what we have to do is, since we fail to reject, then the mean temperature should be what? Still 98.6, right? So the mean temperature of healthy newborn babies is 98.6 Fahrenheit. Okay, so that is our conclusion, non-statistical conclusion. Okay, so basically this is what we do for this hypothesis testing problem. So step one, state the hypothesis. You have a null alternative. Step two, choose a proper test statistic. It's a larger sample. Sigma is known, so we choose this one, and then calculate the value. Find the p-value is the left tail test. So the p-value is the area of the left tail. So that is a probability for the less than this one. So we found that because the p-value is greater than alpha, we fail to reject. There is no sufficient evidence to reject. So therefore, we conclude non-statistically, the mean temperature is 98.6. Right, this rejection reading approach, I'm going to skip here. Okay, now let's consider another one. Okay, so a new cancer medicine was introduced to market 10 years ago, and the company claims that on average, it will prolong a patient's life for 4.3 years. In a study of 89 patients, the average prolonged life is 4.6 years, with sample standard deviation s equal to 1.1. Do the study's data show higher average prolonged life? Okay, so assume significant level, alpha is 0.01, and we want to find this. So how to do that? The first step is very important, right? So you need to be careful. So what is, okay, so firstly, let mu be the mean prolonged life. All right, prolonged life. So the null hypothesis will be what? Will be contains equal sign, right? It's about the population, right? It's about population. So I think this 4.3 is on average is for all the population. So that is mu equals 4.3. It's not 4.6, right? The 4.6 is a value about what? About the sample, 89 patients, right? So the claims, the hypothesis is always about the population. Okay. Versus what? The alternative is mu what? It doesn't show a higher average prolonged life. So that means what? Mu is greater than 4.3. Yes. Okay. So this is the hypothesis. And do we have a larger sample? N equals 89 as greater or equal than 30. And sigma, do we have sigma? Sigma is unknown. So the test statistic is z equals x bar minus mu of 0 s over square root of n. So we are going to use this one, right? So now let's just calculate this value. Z equals, okay, x bar minus mu of 0 s over square root of n. This equals what? X bar is 4.6 minus 4.3 over s is 1.1 over square root of 89. Okay, now again, let's calculate this value. All right, on the top, that's 0.3. Over the bottom, I need to use my calculator again. All right, 11, 1.1. 1.1 over 8.5. Okay, so I got this is 0.1166. Okay, so then 0.3 over 0.1166. Okay, I got this is 2.573. 2.573. All right, so now let me just go ahead and find the p-value. So now to find the p-value, we need to determine is what? A red-tailed test. Okay, the test, it is a red-tailed test. It's a red-tailed test, hence the p-value equals the probability for x is greater than 2.573 equals normal CDF 2.573 10 to the power 99 0 1, and we can calculate this value using our calculator, right? So all right, just 1 second, let me just find the value here. 2.573. Good. Calculate. Okay, I got this one is 0.005. 0.005. Okay, so this is my value. Now, then, well, why this is true? Because again, in our previous, okay, in this one, right, it is a second, it's a right-tailed test. So the p-value is this area. So that's the probability for z greater than z, right? So that's what we have here. Okay. Oh, here, right? That's what we have. It's greater than that. So then draw a conclusion. Now we have the alpha value is what? Is 0.01. Okay, so since the p-value is, well, this is 0.005. This is less than alpha equals 0.01. All right, so we what? If it is less than alpha, we reject H0 in favor of HA. That is what? This is statistical conclusion. And for non-statistical conclusion, it's going to be what? That's going to be, does the data show? Yes, right? The data show higher average prolonged life. Okay. The data do show higher prolonged life than 4.3 years. Okay, I say that, right? So here again, this is a red-tailed test, and we did everything similarly, right? State the hypothesis, choose the proper test statistic, calculate the value, find the p-value, draw the conclusion, both statistically and non-statistically. All right, let's go skip here. Now, let's consider a final example here. All right, the mean salary for all men in a certain profession is $61,253. A special interest group thinks that the mean salary for all women in this profession is different. They randomly select a group of n equals 42 women workers in this profession and obtained a sample mean salary of $59,559 and a sample standard deviation of $2,956. Is there sufficient evidence in the sample to indicate at 5% significance level that women in this profession have a different mean salary? Okay. So let's do this one here. Okay, firstly, let mu be the mean salary of women in this profession. Okay, so the null hypothesis is going to be what? There's no difference. All right, so no difference means what? No difference with from main, right? So that's going to be mu equals 61 to 53. All right, versus now HA, that's what they believe. They think this is what is different. They're not saying it's greater or less. They just say different. So that means what? The alternative is not 61 to 3. That's our alternative. Now, do we have a larger sample? N equals 42 is greater or equal to 30, and sigma is known or not? The population standard deviation is unknown, right? The population standard deviation is unknown. Sigma is unknown, right? So hence we're going to use z equals what? X bar minus mu 0 s over square root of n. Okay, so now calculate the value z equals, okay, x bar minus mu of 0 s over square root of n equals x bar is okay, so we see that this is the sample mean, right? So 59 minus 61, what? 253 over S is 2956 over square root of how many of them? So 42. So square root of 42. Now this one equals, okay, I need to calculate the value again. Just bear me with 1 second. I'm going to get that for you real quick. Okay, so this is 59,859 minus 61, 253. Okay, that's a negative on the top is negative 1394. On the bottom is 2956 over 42 5, okay, 456.121. Let me say that. Okay, so this one equals what? over 456.121, which gives us 3.056. Okay, so this is my negative. Okay, this is negative. Okay, so negative. Now to find the p-value, we need to do this is a two-tailed test. All right, so for two-tailed test, what is the p-value? Let's just check that, right? So we have that here. For two-tailed test, right? Firstly, find the absolute value, and then the p-value is twice the area to the right of this absolute value under the curve. So it's basically 2 probability for z greater than the absolute value of z. Yes, so that is what it means. Okay, so we're going to just use that. Okay, here we go. So hence the p-value equals 2 times the probability for z greater than absolute value of negative 3.056 equals 2 the probability for z greater than 3.056. All right, so because the absolute value of negative is positive, so it's 2 times normal, okay, calculator, right, CDF, 3.056, 10 to the power 99, 0, 1. Okay, so now let me just use this a calculator again to find this value. Oh gosh. Oh gosh. We'll do that. Normal calculator. Okay, so it's going to be okay, so I found that this is 0.002. Okay, so 0.002. Okay, now this is our p-value. So now since what? Okay, I believe this significant level is 5%, so 0.05, right? So since the p-value is less than alpha is 0.05, we what? Reject, right? We reject H0 in favor of HA. This is statistical conclusion, and non-statistically means what? The mean salary for women is different from men, right? So the mean salary for women is different from that for men in this profession. Yes? Okay, so that's what we mean. Okay. All right, I think that's all for this one. And thank you for your attention. I will see you in the next time. Bye-bye.